Hello, everyone. Today we'll be presenting a paper called Incentive Mechanism Design for Unbiased Federated Learning with Randomized Client Participation. This presentation has been prepared by myself, Chedi Morchdi, Yufeng and Parth Tusham. So first, let's take a look at our agenda for the presentation. First, we're going to take a look at the background, some important key concepts. Then we're going to take a look at the contribution of the authors in this paper. Then we're going to take a look at the methodology and finally some experimental results. So the first key concept here that we need to know is federated learning. So basically, what is federated learning? I think most of us have heard this term at least once. So federated learning is about multiple clients training a machine learning model, a shared machine learning model, without actually sharing the raw data. So how this happens is that each client trains the model on its own local data, then only sends the model updates to the central server and not the entire model. So there are some advantages to this. So first, federated learning would preserve privacy since the clients keep their data local. This would reduce communication costs since the clients only send the model updates to the server and not the entire model. And also, this would benefit the model since it would learn from diverse distributed sources. So basically, the main takeaway from federated learning is that it trains a shared machine learning model across different devices without sharing data. We can illustrate federated learning with a simple example. For here, it's the cooking club example. So here, suppose we have a cooking club, we have a club host. This club host has an initial recipe for some dish. So this club host would give that initial recipe to all of the members, to the members of the cooking club. And so the initial recipe here, by analogy, is a machine learning model, and each member is gonna take that initial recipe back home and try some tweaks in their own home kitchen to try to improve that recipe. So, for example, we have three members here, Alice, Bob, and Carol. After experimenting back at home with the recipe, Alice could suggest adding one spoon of hot sauce. Bob could suggest reducing the salt. Carol could suggest adding one spoon of sugar. So all these members would take their suggestions and give it back to the club's host. And the club host would aggregate the suggestions and update the recipe. And this would keep going on recursively until we reach a final satisfying recipe. So this is an analogy to what's happening in federated learning. Another key concept that we need to know here are incentive mechanisms. So basically, federated learning relies on the clients to update the model. And to update the model, clients use local resources, which means that they incur costs. Also, the clients might not just be interested in the model at all, so they won't be interested in training it. So here, the host would need to incentivize, basically give money, services, something like that to ensure that the clients participate. So basically, what we need to know about incentive mechanism, the takeaway is that clients basically won't help train the model unless there's something in it for them. An example of incentive mechanism would be that cooking club host would offer, let's say, brownies to whoever participates in tweaking the recipe. Uh, Now let's talk about client participation. So there are two types of client participation. First type is full client participation. Basically, here all the clients participate in training the model. This setting is a little unrealistic because it's hard incentivizing all of the clients because this would cost too much for the host. And also, some clients might not be available for some training rounds. So this setting is unrealistic. Forget about it. We're not going to be talking about it. Now, for the other setting, which is partial client participation. So here, only a few clients participate in training the model all the time. And these clients are fixed. It's always the same clients. and they are chosen based on the quality of the resources. But one drawback of this would be that this would lead to training a heavily biased model since it's the same clients every time. An example of why we would run into bias would be if imagine if only people who liked spicy food participated in tweaking the recipe, then we're going to end up with a recipe that is biased towards spiciness. So basically, the main takeaway here is that existing client participation types are flawed, which calls for designing an unbiased federated learning partial client participation incentive mechanism. Here, notice that we said partial client because we've already discarded the full client setting. So basically, now let's talk about the contribution of the authors. So basically, the research questions that these authors asked. So to achieve the previously set goal, authors suggested to explore two things: the client's independent participation levels in incentivized settings, and also how to efficiently incentivize clients based on their participation levels' impact on the model. So basically, to do so, the authors introduced two concepts here. First is the intrinsic value. Basically, this means that the client might be interested in training a model for reasons other than monetary incentives. For example, that this client would benefit from the good quality of the model. And also the concept of bidirectional payments, meaning that the client might end up paying the server if his intrinsic value is significant. An example of both of these concepts is that a member of the cooking club might be so interested in the final recipe's quality that he is, let's say he's going to use it at the end, that he would end up paying the club host to be included, to participate in tweaking that recipe. So basically, the main contribution is that they proposed an unbiased incentive mechanism for federated learning with randomized client participation. So this is an incentive mechanism leading to unbiased model training with randomized client participation. Here, the payments are customized based on each client's participation level and intrinsic value, and the client-server interaction is modeled as a stackable game. We should probably mention here that the client's participation level is basically just the probability of this client participating in training the model. Another key concept that we should know is the stackable game, and really quickly, it's just a two-stage game between a leader and a follower. The leader first tests some rules, and then the followers would react optimally to the leader's rules. And now I will give the word to my colleague Yufeng to talk about the methodology part.
Hello, I'm Yufeng. Let me introduce the methodology of this paper. Through this paper, the author proposed to use equation 1 to maintain unbiasedness during participation local updates. And as we can see that to maintain unbiasedness, we need to know the participation level Q. To achieve this, we need the following setups. The first one is the server need to maintain a price vector P for each client to incentive client's participation, and the participation level vector is denoted as Q. In that way, the server's decision problems can be reformulated as expression 4, where we still minimize the expected loss, but we need to ensure that the total payments to the clients should be strictly less than or equal to total budget B. For the client side, we first model the local cost as a quadratic function in terms of participation level. The intuition behind this is the higher participation level, the higher cost it will be. And we also model the intrinsic value as the improvement of model due to the participation. And the Wn star here denotes the local optimal parameter. So that way we denote the client decision problems as we maximize the utility function by optimizing the variable Qn, and the utility function is defined as the total payments we receive from server minus the local cost plus our intrinsic value. And we need to ensure that the participation level satisfies some constraints. So that way we can formulate the Starkberg as the bilevel optimization problems expressed in equation 6, where arrows the upper optimization problems is the client decision problems. But we notice that the participation level also dependent on price vector, where we need to obtain such optimal price vector by optimizing the inner level problems, which is the server's decision problems. But directly solving these problems still encounter several challenges. First is that the expected loss contains randomness from participation level Q and the model parameters obtained after several rounds of local SGD at each client. And we cannot know the value of expected loss unless we train the model and also obtain the model parameters. And there is no analytical expressions for the expected loss. So the conclusion is that we need to find a surrogate value to estimate the expected loss. Under made assumptions, the author established the inequality 7, which says that the function value gap between expected loss with respect to the optimum can be upper bounded by a constant averaged over R rounds. But notice that the right-hand side of this inequality does not depend on model parameter at R round, which is easier to compute. Through this way, we first transform the client decision problems in Form 8, where we just replace the expected loss by its upper bound estimation. And the authors claim that this problem is a concave programming problem, and the optimal solution is unique. Additionally, we can obtain the expression of price in terms of Q, and we can utilize them to transform the server's decision problems as following. We first replace the expected loss by its upper bound estimate obtained from convergence analysis. And we also replace the constraint Pn by its expression in terms of Qn. And through that way, the server's decision problems transformed into an optimization problems in terms of Q. And under milled transformations, this formulation 9 can be formulated as a convex optimization problems, which can be efficiently solved by software CVX. And once we obtain the optimal participation level, we know the optimal price for each client. And the author also explored additional relationship between the optimal price vector and the participation level Q. The first observation is that the total payment to clients should be tight, which means it should be equals to the total budget. And additionally, if budget B increases, the price P and the participation level Q will simultaneously increase. That means if server's budget is higher, it should set higher price to incentive client's participation level. And under made assumption, the author also built equivalence relationship between client IJ, and it reveals that the clients with larger data heterogeneity should have larger participation level, and the clients with large local cost should have lower participation level. And similarly, the clients with a higher intrinsic value should have lower participation level. Through theorem 2 and 3, the author further reviews the bidirectional payments mechanism through clients and servers. It means that there exists a threshold Vt such that for any intrinsic value smaller than the threshold, the server should pay to the client. And for any intrinsic value larger than the threshold, the client should pay to the server. Additionally, under made assumptions, uh, the author builds relationship between intrinsic value and the price. Reveals that the clients should pay or receive larger price to server if it has higher local cost, and the condition whether it pay or receive depends on the respective value compared with uh, the threshold. And most importantly, it reveals that the client benefit less from server if they have higher intrinsic value. At last, I summarize the final takeaways from the theoretical deductions. Server's price is correlated with client participation level, and the incentive payments between clients and the server are bidirectional, meaning that there exists the possibility that the server pays to the clients, and there also exists the possibility that clients pays to server. And from server's perspective, server should set higher prices for those clients who have larger local cost. And from client perspective, the clients with higher intrinsic value should not participate in model training. Next, let my group mate pass to Tusham to introduce experimental result for this paper.
Thank you, Yufeng. Now let us begin by walking through the experimental setup. So we have 40 Raspberry Pi clients acting as the edge devices, one central server hosted on a laptop, and a Wi-Fi router which simulates the communication over a local network using TCP. So we use three data sets to evaluate, namely the synthetic data set, the MNIST data set, and the EMNIST data set. They represent the increasing level of data complexity and heterogeneity. So the goal here is to compare three pricing schemes: uniform pricing scheme where every client gets paid the same. The weighted pricing scheme is based on the local data volume, and our proposed optimal pricing, which adjusts based on each client's cost, data quality, and intrinsic motivation. Now, to better understand how the system behaves under different conditions, there are three experimental setups. We can think of it like the cooking club analogy I introduced earlier in the presentation, where some guests bring in suggestions for the main recipe. Setup one simulates average guests. They contribute fairly and expect average rewards. In setup two, the clients are passionate and they are highly motivated and even contribute without high compensation. In setup three, the guests they need strong incentives to participate, but their contributions are so valuable. So each setup tweaks the parameter of the budget, cost, and client value to model real world variations. Now, the key question is, can we design an incentive mechanism that improves both the model performance and client satisfaction while staying within the limited budget? The answer is yes, as we'll see in the next few slides. So let's talk about setup one, which is using the synthetic data set. So in setup one, we observe fast and stable convergence when using proposed pricing. The loss reduces quicker and the accuracy reaches 72% earlier than the uniform or the weighted schemes. This confirms that even in moderately constrained settings, our pricing mechanism performs better. It's like a standard club meeting where most members contribute fairly and consistently. In setup 2 is a particularly interesting because it models clients with very high motivation but minimal compensation. Even under these conditions, our pricing reaches 89% accuracy in just 411 seconds, which is much faster than any other baseline. So it looks like the guests who deeply care about the final recipe show up enthusiastically, and even if they're not being paid much. In setup three, we deal with high cost, moderately motivated clients. So despite this challenge, the proposed pricing mechanism outperforms both baseline and reaches 69% accuracy, significantly faster than both weighted or uniform pricing schemes. This proves our model can adapt even under expensive participation and we can think of it like convincing that one picky guest to contribute by offering a really good incentive. Here, we try to isolate the effect of increasing intrinsic value using setup one. So as V increases, the clients are more willing to participate, which in turn improves both accuracy and decreases loss. What's remarkable is that when clients care deeply about the final recipe or the global model, they engage even without compensation. It's like the club member paying to join because they want to perfect the recipe. Next, we examine what happens when we vary the local costs in setup two. So the results show that lower costs yield smoother and faster convergence, and higher costs discourage clients from participating, which directly impacts the model quality. This aligns well with our theory and fits our analogy. If cooking is too resource heavy, some guests skip the session. So now in setup three, we vary the total budget as expected. A higher budget allows more clients to participate at higher levels, which boosts model performance. And it's like the host offering better ingredients and rewards, and more guests show up to help the final dish improve dramatically. Now, coming over to client satisfaction. So this is a pretty key part of federated learning, and our table shows that client using the proposed pricing scheme gains significant utility, especially in setup two, where the clients are passionate. And this just isn't just efficient for the model, it's also fair and rewarding for the clients. The the participants who care more and contribute more, it's just like enthusiastic cooks get appropriately recognized. Now, coming on to parameter sensitivity, to summarize, the behavior across all setups, the higher the intrinsic value makes a client more likely to engage. So the lower cost increases participation and a higher budget broadens the client involvement. These three variables, V, C, and B, capture most of the incentive dynamics in our system and reflect how we can keep the cooking club balanced, fair, and productive. So some unique insights from the mechanism. So here are some surprising behaviors we observed. Some clients actually pay the server to participate. So high cost clients are compensated more to balance the effort, and freeloaders are automatically discouraged with lower rewards. These behavior aren't hand coded; they emerge naturally from the Stackelberg game setup that we introduced earlier. So here are some limitations. So the system isn't without limitations, and we assume that the server knows each client's cost value, which may not be always realistic. So the model also assumes convex cost function and doesn't yet account for client dropouts or communication overheads. These are areas for future improvement, or as in the club, better for logistics and planning. Now, some key takeaways from the paper. So if there is one thing to remember, it is this. Incentivizing participation in federated learning isn't just about paying more, it's about paying smart. Now, coming on to conclusions. To conclude, our proposed mechanism leads to faster, more accurate training while maintaining fairness and flexibility across diverse client types. It moves federated learning closer to the real-world deployability by including realistic incentives and adapting dynamically to participation conditions, just like running a successful fair and a tasty cooking club. Thank you.